Okay, so in my office today, there was a question about why we were able to separate um, rational numbers with powers of things in the denominator the way we do when we use integration by partial fractions. So remember, the way we separate it is we take that x. So right now it's x plus 2 to a power. So we write in all of the back powers up to that power. In this case, I just have the powers equal to 2. And then, of course, whatever factors are there. And well, of course, if this is a proper fraction, so, this is a cubic in the denominator, so some sort of second degree or smaller in the numerator here, making it a proper fraction. If we were to have something like this, well, what I would need is for this x plus 2 term, we have a constant and a constant and a constant because all of the factors are linear. Now, the question was, this factor here isn't really the most general proper fraction, because if you notice, that's a second degree polynomial in the denominator, which means I could theoretically have a numerator, a linear in the numerator, okay? But the fact that we have this part here, that first term, those two together will combine to be a proper fraction with that x plus 2 squared in the denominator. So let me first note what's happening here. Okay, so let's take this and let's look at it more generally. Really, there's two distinct factors, right? There's the x plus 2 and there's the x minus 1. The problem is, if these were the only two things we'd have, then when I added these, the common denominator I would get would be x plus 2 times x minus 1, which is, that's an x minus 1 there, which is not enough. I need an x plus 2 squared, right? So I need at least one factor to have an x plus 2 squared in it. Okay, so let's put that there. Let's suppose we just have one. In this case, like I said before, the most general way we could do this and have them be proper fraction is if I have a linear here, a general linear here, and just a constant here. Since that's linear, this has got to be degree 0 or less. And then you add it together and you get your degree 2 or less polynomial up here, which happens in this case to be 2x squared plus x plus 1. But the problem is, this thing here, this ax plus b over x plus 2 squared, might be sort of a drag to integrate. And it can be simplified to something that looks like those. And those we know how to integrate. So let me just show you how you simplify it. I'm going to take my ax plus b, and I'm going to add and subtract what I need to, so that when I can separate that fraction into something where the x plus 2 will factor out. So in other words, I want to add a 2a and subtract a 2a. Because if I do that, then I'm going to have a times x plus 2 over x plus 2 squared plus this negative 2a plus b over x plus 2 squared, which of course simplifies to a over x plus 2 plus this thing b minus 2a over x plus 2 squared. Okay, the point here is that this thing I've just done here is basically exactly the same thing as what I have up here, because a is just a general constant. That's what my a is. And what's my b going to be? My b is going to be this whole thing here, right? So it's a constant over x plus 2 plus some other constant over x plus 2 squared. So when I make this fraction, the most general way I can put a quadratic in the denominator when you have a square like that, I do end up being able to separate it like this, and since this is easier to work with, that's how we usually write it. Now, let's look at it a little bit more involved, because we had done something like this in class to show why we have done that way. We didn't do the other ones in class, so let's look at something else. Let's suppose now I have a cubic. Oh, let's undo that and make that a skinnier line. So suppose I've got a cubic in the denominator. X plus 1 cubed, and then of course let's put that other factor in just so we have something to balance it out. Let's make it an x squared. Okay, and then of course that's going to be what, a 5th degree polynomial, right? So we need some polynomial in the numerator of degree less than or equal to 4, right, to be proper. And if we do that, then we've noted that, of course, I've told you in class the way we separate this is we write it as x plus something over x plus 1 plus something over x plus 1 squared plus something over x plus 1 cubed plus something over x squared plus 2, which doesn't factor anymore, right? Now this x squared, well, the way we've been doing it in class is, well, the most general way to make the x plus 1 in the denominator proper is to have a constant in the numerator, but we continue just writing a constant in the numerator over these, even though we have a quadratic here and a cubic here. This one, of course, we're going to have a linear. The most general way to make this is a linear in the numerator. Okay, so this one here is not the issue we're talking about today. Let's look at these other 3. So the idea here is in these other 3, this is the same thing as writing something like this, x plus 1 cubed with a degree, that's a cubic, so a 2nd degree in the numerator. And you can see that where this is the most general 2nd degree you can get, and you can see that by simply adding those fractions and seeing that if I add these, I indeed get a 2nd degree in the numerator, and it's as general as it can be. So when I add these, let's just look at what the numerators are going to be. I'm going to need an x plus 1 squared here, and I'm going to need an x plus 1 here, and I don't need anything with that c, right? So that's just the numerator of what I get when I add them, right? And let's expand these and combine like terms. So I'm going to get a ax squared plus 2ax plus 1. So I'm going to have 1ax squared. 2ax, I'm going to have a bx, so that's going to be plus 2a plus b x. And I'm going to have a b, and a c plus a plus b plus c here. Now clearly we have a 2nd degree in the numerator when we add those. Now the question is, can this be as general as we want? Well, yeah, we can make this. This is a general 2nd degree polynomial. A can be anything, right? We're choosing A arbitrarily. Once we choose A, whatever we want the 2nd term to be, we choose B correspondingly. So if we wanted that, say we chose A to be 2, then we could, and I wanted the 2nd term to be 10, well, that would mean that B would have to be 0, right? Or would have to be 6, right? 2 times 4 plus 6 is 10, right? And once I have B and A chosen, this is just going to be some constant. I can choose C, whatever I need it to be so that this can be anything I want. In other words, I have just an arbitrary quadratic polynomial in the numerator. And so writing this here with this expansion is the same as writing x plus 1 cubed in the denominator with an arbitrary quadratic polynomial in the numerator. The same thing happens if you have a 4th degree or a 5th degree or a 6th degree. And the same thing, let's just look and see what happens when the thing that you're squaring is not linear, it's quadratic. So let's go through here again. So I'm not going to write all those other factors in, but I've got something that looks like, let's say, 1 plus x squared here. Of course, this is what degree? That's going to be a 4th degree, so the numerator here would have to be a 3rd degree polynomial of or less, degree 3 or less. Now, assuming there are other factors, because if there's not other factors, it's kind of pointless. But we mentioned in class that we would write it like this. And the thing in the numerator is going to be the most general thing to make the original factor in the denominator a proper function. So I would need a linear in the numerator. But we keep with that linear in the numerator in the second one too, even though that's a 4th degree in the denominator there. And just to point out that we actually get something that's a general 3rd degree in the numerator over this 1 plus x squared in the denominator. Let's just see what the numerator will be when I add these things. Of course, I'm going to need to. The numerator of the first fraction is going to be ax plus b times this 1 plus x squared. And the numerator of the second factor, when I add them together, is just going to be cx plus d, because I don't need to multiply that by anything. And multiplying this out, I get what? Ax cubed plus bx squared plus ax plus b, right? And that's plus cx plus d. And let's combine like terms again. That's going to be ax cubed plus, there's only one quadratic term, bx squared. And there's 2 linear, a and c, a plus cx, and 2 constants, b plus d. Okay, as you can see, I get a cubic here when I add those in the numerator, but the point is I get the most general cubic possible. Any cubic I want, I can get by choosing my a, b, c, and d correctly. Of course, I can choose my a to be anything, whatever the coefficient I want on the x cubed here, and I can choose b to be whatever the coefficient I want on the x squared to be. Once I have a chosen, I can choose c so that this coefficient of x is going to be anything I want it to be. And once I have b chosen, I can choose d so the constant is anything I want. So it's the most general cubic possible. And that's the point here. It's just that the way that we do it, when we do integration by partial fractions, the way that we actually do it is easier to integrate this and this than it is to integrate this with a cubic on top. That's why we separate it. Okay.